in some wrong places. Okay, all right, that's fine. All right, and so when the
small window.
Okay, perfect then. Okay, so I guess our challenge, in fact, is and these models are very expensive and to run. Practically, the problem is not only limited by the computation itself, but also limited by memory bandwidth and data movement and so on and so forth. So what we going to do? Okay. The central idea of this talk, in fact, is we find we don't have to run outworks at every step. What do I mean over here is when we observe and across in different systems, very obvious and observation showed us is there's a huge redundancy in tokens and neurons and experts and frameworks and times and even weight representations. Definitely it's everywhere. So if we are able to identify the key information and skip the rest, we could dramatically improve the inference and efficiency. That's the core idea I want to convey in this talk. And particularly, I will cover 4 different topics today. First, the sparsity structures and for inference and acceleration across large language models and vision language models. Second, evidential keyframe samplings and for long-form visual understanding. Third is latent bridge and for vision language action model acceleration. And the 4 actually is an architecture solutions and hardware solutions. EVA basically is an vector quantization architecture, and we designed that particularly for the decoding phase acceleration. So again, the key idea over here is all these technologies we hope eventually help us and goes to the future where powerful AI models and can be deployed and run on edge devices, and that's our research goal. So let me jump into details, and the first part is talking about the sparsity. Sparsity is in particular for the large language models and the vision language models. Okay. In fact, in the past, and I guess one of the most important observations we had is these foundation models are naturally highly sparse. So there are 2 forms of sparsity technologies. Okay, one, static and sparsity, basically removes a fixed set of weight parameters or connections and after training. Very effective and in practice, however, it's usually limited by the pruning rate before the accuracy, the performance, and starts to suffer. Dynamic sparsity actually is more powerful. Okay, so instead of applying an fixed or uniform the network structures into all input, the concept of a dynamic sparsity basically is saying like activate different components, depending on the tokens and being processed. Okay. So what we find essentially is in dynamic sparsity potentially can reduce a large portion of the computations while still maintain models and quality. So for instance, in our data here illustrate that in the analysis and for large language models and demonstrate it could impose up to 80% and 95% sparsity on attention paths and multi-level perception neurons respectively without hurting the performance in March. That's essentially demonstrating great potential for efficient inference and at edge, where resources are highly limited. So why does it matter for speed? In fact, if you go to any hardware system conferences or platforms and people captate saying like in the inference of large-scale models is fundamentally memory bound, or we show here I/O bound instead of an compute bound. So the dominant cost come from loading those massive model weights and from lower level memories, rather than performing arithmetics. Okay, so if dynamic sparsity can help and limit the weight selection to a very small portion, and then we can directly reduce the memory traffic. And of course, a lower memory requirement indicating lower latency, lower energy, and particularly improve the performance and for edge implementations. So from this perspective, and we claim that and sparsity is not only a models and property, it is indeed hardware opportunity. Well, another important form of sparsity, in fact, is in the activation sparsity. So for a given input, and if you're really observing the activations and through the forward network, it turned out and only a small portion of the neurons and will be actively and contribute meaningful outputs. Okay. So again, if we are able to identify what neurons will be activated, then it can help to reduce in computation cost and and many others. So in the past, the previous approaches and usually developed in a small network to estimate an activation patterns, which usually introduce additional overhead. Okay, so we propose and call core inferior based on the observation that an activation sparsity is strongly tied to input semitext in terms of both in similarity and the stability. Okay, so we propose a framework that activates neurons and based on the input semitext predictions. And the short video over here already show that, and we can significantly speed up the operation at a single GPU and make the operation and response and within people's expectation time. Well, what else then do we have? Okay, in fact, then the sparsity is also very obvious and observed in vision language model as well. So in this case, and for instance, and for giving image, and we ask a number of the questions, I guess, and these are too small to say, right? If you trace and again the data patterns and only a small portion of the vision tokens will be useful and contribute to the final result. Largely those in vision and image tokens and contribute very little to the final decisions. And therefore that incentivizes to propose and what we call the core matching. It's a co-adaptive and sparse inference and framework leverage and token pruning technologies. And as you can see, as far as we can identify those most informative tokens, and we are able to, again, have a better performance efficiency while still preserve the accuracy. Well, another particular situation we have actually is the visuals, and the redundancy is very severe in visuals. For a lot, any video clips, and it's easily to have hundreds of frames and tens of thousands of tokens and at least, right? What is obvious and observation, in fact, is not all the frames in a video are equally important or relevant to the inquiries. And so, for instance, if the question is very general, like illustrate over here, and then, of course, analyze this and need to cover perhaps the entire video. But more common situations, in fact, is very specific questions and related to certain details. For instance, in the green question requires information from frames in 31 and 39 only, and the blue ones can be precisely answered by referring frame 56. So I guess the approach is very important to identify those keyframes we call, and also identify the key vision tokens and from those frames. So we proposed an KVTP, keyframe oriented and visual token pruning. Okay, how does it compare with existing approach? Okay, existing actually methodologies and usually refers to one of the two common strategies. One is, and we call it unconditional token prunings. It's essentially treat every frame equally and then assign the same pruning rate into all these frames. And another one called hard frame selection. Okay, so primarily focus on the frames, and it's preserve only the key frames and discard all the others. So as you can see, both methodologies and have limitations, right? For the token prunings, and it's causing significant information loss in those key frames because the information offered by different frames are not equal. Well, for the keyframe selections, and it breaks the temporal and the context and connections across in different parts. So KVTP we proposed and introduce adaptive pruning rates and based on its relevances to the query content. So essentially, we apply different or adaptive and pruning rate on different frames, and you can imagine for those are not necessary. In fact, 100% it can be removed. Well, with those and very important, we maintain majority of that. But for some others, we can still have some relevant information, and so demonstrate a better trade-off in between efficiency and performance. Well, so far I basically discussed the activation sparsity and token sparsity separately. But if you work in this domains, one observation in fact is activation and the token sparsities naturally interact. And this is also from our work of a quorum matching. What we find is that important tokens tend to active and important core neurons. In other words, that motivate us to have a more unified approach. Basically, we could identify the core neurons and also retain the critical tokens. So the scheme together help us to accelerate in both the pre-refilling stage and the decoding stage and simultaneously. I roughly show some result over here. So across in different models and different frame budgets, and the first two bars actually corresponding to the baselines, and the following three groups and represent the different configuration trade-offs. But generally speaking, as you can see, we speed up in both in profiling and decoding stages, and the balance depends on the configuration trade-offs. Another important part actually is related to the similarity, or we call it structured and sparsity. Okay, so in fact, then if you observe the images and more important in the visuals, and you could find high similarities. What do I mean over here is similarity can be considered as structured and sparsity, right? And while we observing particular videos, and we observe two types of important similarities. One is what we call the blockwise and similarities, basically nearby tokens and shows high similarity temporally and spatially. Okay. We also identify the finer vector-based and similarities, and especially for the visuals when we have motion situations, right? So by observing this, and we actually consider anything we can do at hardware level in order to accelerate in such applications. For blockwise and similarities, and in fact, and since those tokens are close by again spatially and temporally, and we are able to conduct the local matchings and remove redundant computations. Well, for vector-wise based, and it's basically can be aligned with matrix and matrix multiplication tiling structures in hardware. So I don't have to explain the hardware much over here, but the key over here is at a finer granularity levels, we could conduct the matching structures and reduce the use of the computation components. Okay, so the corresponding architecture solutions is called Focus, which is a lightweighted and streaming architecture that detects and exploit the redundancy or the similarity I mentioned. Okay, and we designed the architecture based on systolic and array structures, and so the focus unit again primarily focus on the finer vector level similarity detections. Okay, so without much details and quickly showing like in the structure across a very large different variety of benchmarks, and we're able to improve then speed up the executions in more than 7 times and energy efficiency on average and more than 10 times. Okay. All right, so this is the first part, and I like to move to the second part and evidential keyframe samplings and primarily for the visual understanding. Okay, so considering again when we have a long form visual and when we have some questions over here to answer. As I mentioned previously, usually only a few forms in here contains the evidence and that's necessary to answer the questions. So everything else actually is a context and for the particular queries and our goal in fact is to identify those useful and relevant in the frames. So if we're able to do this, and again, we're able to reduce the computation cost, and therefore we name it as an input evidence and sparsity. Okay, so back to the methodologies, and then how are we able to find those in frames and automatically, right? We formulate the keyframes and selection as a mutual information problems. And in fact, then ideally, the expectation is and we select the frames and that maximize and the mutual information. So in other words, and our goal is to select and those most relevant frames and not like those looks important visually. Okay, so more specifically, we set up the upper bound constraints over here and simplify the structures and to what we represent over here. It's basically prioritized in the frames and that have the highest mutual information correlations and here. So while we are doing this, and another critical question, in fact, is and how can we estimate the evidential values? Okay, so particularly here we developed what we called query conditioned evidence and score network, which is composed of 4 key parts. The first part actually is in the shared vision language encoder that match the frames and queries in a common representation space. The second part is called temporal module, and that is used to capture the motion context. The third part actually is in query guided and evidence and gating. Essentially, with query informations, and we can remove irrelevant informations and reduce the computation cost. But more at the end, we have this in evidence and score heads, and the goal over here is to give out the scores and of each frame, and of course, and the frames and is defined how useful this frame is for answering the specific questions. Okay. So the page over here actually given the table of an evaluation results and which in fact demonstrate a consistent improvement across in different models and the different frame budgets. So particularly if you're looking at the improvement on LV benches, constantly it's providing 8 to 10 points in improvement. And specifically, we like to highlight even when the frame budget is not very high, the output result is still kind of promising. The qualitative and evaluation actually provide a similar story over here. Essentially, the result is seeing like if we are able to identify the more evidential frames and then the result is more accurate and more reliable. Okay. So this is the second part, and the third part I wanted to introduce is called the latent bridge, and for the VLA model acceleration. And in fact, and this is our collaboration with our Qualcomm supporters. And okay, so when we move from large language models and to vision language models and then to vision language action models, and particularly, one interesting observation we find is in the bottleneck in many VLA executions and is the VLM backbone models. So for instance, in one single VLM execution can take in tens of a million seconds, and which is pretty long. So how can we improve the performance? How can we really reduce the latency? Well, that's back to what I talked at the beginning, the core idea of this talk. In fact, perhaps we do not need to run the model all the time. Maybe we could replace the backbone VLM model with some simplified, what we call the bridge model. So we introduce this lightweight and latent bridge. It's used to predict how the latent representation evolves over time. Okay, so the structure over here, for instance, and we have one VLM, we run once of this VLM model, followed by a few bridge model calls, and then we can call the VLM again to bring the performance back. Okay, that's the essential idea. And by doing this, as you can see, we can eliminate a large portion of the calls of an VLM. Well, the bridge call only takes in a few milliseconds, and so we can improve the inference time. So how to train the bridge? We formed this in 3-stage pipelines to realize this. And the first stage and basically collect the trajectories and using the original VLA pipeline. And the second part, we train the bridge offline to predict the latent update. And the third part, in fact, is applying dagger structures and to expose the bridge to its own prediction and then reduce the deployment error. Okay, so okay, I wanted to emphasize, and of course, the training of this pipelines only takes a few hours in a simple, like not super powerful GPU setups, and we can apply the same recipes for every benchmark. Well, let me get into the result quickly. The result is pretty encouraging. Actually, if you can see those in small fonts, and we achieve in 1.5 to 1.7 times in speed up, and while the other matrices remain very close or even better than original VLM VLA based solutions. Well, one observation is the feature catching kind of fails badly. So why? This is because in the bridge predicts and feature involvement, it's not just a simple call those installed features. So we wanted to highlight this is the key difference of our structures and from like simply VLM acceleration structure. Okay. This page actually basically seeing like we did more application studies and the performance remains good. But there's some highlights and I wanted to bring it out. Number one, dagger is critical. Number two, fresh visual information is essential. In fact, the size of our bridge part is not very critical. In other words, the conditional signals and the training strategy is very important, but the bridger models and capacity is not that. So why is it? This page actually giving more information. And the curve, the blue curve here is for the feature catching I mentioned previously. And as you can see, it shows the drift away from the truly representations. Well, our schemes in kind of a trace in the VLM solutions and better. Okay. We do have more over there, but essentially, we combine the prediction by bridge and the VLMs and calling that periodically as to balance the efficiency and the accuracy. Not so sure I have time for the EVAs, and it's again architecture level solutions. And in fact, then again the decoding structures and has been widely recognized as memory and I/O bonded. The reason is, and we need to call the matrix and weight matrices continually to the execution units. So previously, vector quantization recently has been introduced. As by name, you can see that, and the goal is to reduce the precision representation from like in high precisions to very low precision. In practice, however, what we find is it doesn't really improve the performance and accordingly. Because of the computation efficiency, lower utilization of the computation units, and also memory inefficiency. Basically, when we do those lookup table searchings, and it's kind of contracted by the content. So our idea, in fact, is to change the order of the executions. And again, if you do hardware designs, and this isn't quite a straightforward thought, but the straightforward idea over here is to perform weight lookup table first, and then simplify the remaining computations. Okay. I do not have a time, but essentially, as you can see, we are able to achieve an 11 times in speed up and 7 times in higher energy efficiencies in comparison to state-of-the-art architecture solutions. So my main point over here, in fact, is an architecture and hardware solutions need to be co-optimized with existing algorithm solutions. So let me quickly conclude. Okay. In fact, then I gave 4 examples in different angles, but they all represent the same theme here is, and we do believe that large models don't need to perform all the works at every step. The key, in fact, is to identify those essentially important information, and we may skip the rest in terms of the computation, in terms of the data, memory usage, and the data transfers. And we do find, in fact, and there's a huge space for us to optimize and essentially token sparsity, temporal sparsity, compression techniques. And I present them like one by one, but essentially they are orthogonal and composable. So our long-term goal is really to make very powerful multimodal intelligence on edge devices, and very importantly, to offer the functionality at a conversational latency. Again, this is my research goal, and I really appreciate the opportunity today as well. Thank you.